In this video, we are going to study about the central limit theorem. This is one of the very important topic in statistics. But before we study that very special topic, let's first discuss about the sampling distributions and estimators. The sampling distribution of a statistic is defined to be the distribution of all the values of the statistic when all the possible samples of the same size n are taken from the same population, and that could be the sample mean or the sample proportion. The sampling distribution of the sample mean, let's just talk about the sample mean first. This is the distribution of all the possible sample mean with all the samples having the same sample size n taken from the same population. So given a whole population, we take a sample from the population and we keep repeating that sampling until we get a certain number of the samples, and we take the sample means of each of the individual samples, and then that is the sampling distribution of all the sample mean inside that sample, inside that population having the same sample size of n. Now let's quickly look over one of these example here, the first one. So in this case, we have a tetrahedral dice. The dice that has 4 sides. So this die has the shape just like a pyramid with 4 faces, 1, 2, 3, and 4. So each face corresponds to a number between 1 and 4. So you can see here 1, 2, 3, and then the other side is 4. When you are tossing a tetrahedral die, it's similar when you are trying to sampling a value from the population from 1, 2, 3, or 4. Now, this is the whole population, 1, 2, 3, and 4. We can easily find the population mean, mu, just by adding them and then divide by 4. And then you can also, using the standard deviation of the population formula, to also find the sigma to be the standard deviation of that population 1, 2, 3, and 4. So mu and sigma, we can find that from the earlier chapters. But now, suppose that we take the dice and we toss them 3 times. And then the sequence of the 3 numbers observed may be thought of as a sample of size 3 because we toss them 3 times. So we take a sample of the size 3 numbers. Now we may get something like 111. So that could be you are tossing the dice 3 times and you all got the face of 1, 1, and 1. Or you may get 2 number 1 and then the last one you get the face of number 2. Or 2 number 1 and then the last one you get 3, and so on. And then if you keep doing that, you see that we have a bunch of different samples. So this is a sample. 111 is one of the choice that we can get, and then the other one 112, 113, 114, and then 121, and all the way down. This is all the options that we may get. Now for each sample, I go ahead and I find the sample mean. The sample mean is found by adding all 3 of them divided by 3. The sample mean of D3, we take D3 value, we add them 4 plus 1 plus 1, which is 6. 6 divided by 3 give me 2 for the mean. So the X bar is the sample mean of each sample of the size 3. And then we have all the list of the results over using the dice, and then the same thing here, all the way here, and all the way here. We have a total of 64 possible outcomes when you are tossing the dice with the sequence of 3 numbers. So the total should be 64. Each column has 16. So 16, 32, 48, and 64. Okay, so after we took the sample, each sample, and then we found the sample mean, the average value for each small sample from the population, then we got the results that the sample means it targets the value of the population mean. Remember, the population mean we found here was 2.5, the mu value. So after we got all of that sample means for all the size, they tend to approaching to the population mean. And the distribution of the sample means also approaching to the normal curve or the normal distribution. Okay, so here on the y-axis, this is the probabilities. On the x-axis is the value of the sample mean. And if you plot them or using the sample size of just 30, then you can approximately get the normal curve for the distribution of the sample mean. Now, we will repeat the same process, but we will do that for the sample variance and the sample proportion. And we found out that for the sample variance, we will get the figure that has the skew distribution to the right. And then for the sample proportion, we will get an approximation of the normal curve. So we can make some conclusion that the sample means, the variances, and the proportions, they are called unbiased estimator. So for the sample means, variance, and proportion, they are called unbiased estimator. That means their value, they target the population parameter. So the value of the sample means, variance, and proportions, they are going to approach to the population parameter. However, the sample medians, the range, and the standard deviation, they are biased estimator because their value do not target the population parameter. They are different. They are not approaching to the population parameter. Only the mean, variance, and proportion. Okay, let's focus back to the sample of the teacher Hitro dice. Again, we have 64 values for the sample mean. This is the sample mean for all the value of each small sample of the size 3. So now I list them in the table. So 64 different values. Okay, and then I can construct the probability distribution table. So I go ahead and I know that the total should be 64. We have 64 sample means for the count. Now, to construct the probability distribution table, we need the value of the x bar and then p of x bar. So let's take a look at the 1.0. So 1.0, there's only one value of 1.0. So we have nothing else here for 1.0. There's no 1.0 for the second column. There's no 1.0 for the third column. And there's no 1.0 for the fourth column. Therefore, for 1.0, we know that the total we have is 64. So the probability of getting 1.0 is just 1 over 64 or 0.016. And then doing the same thing for 1.33. 1.33, we have 1 right here, another 1 here, 2, so nothing here, and then another 1 here, so we have 3, and then the third column we don't have anything, and then the fourth column we don't have anything, so there's only 1, 2, and 3 out of 64. So the probability of getting 1.33 is 3 out of 64 or 0.047. And if we keep doing that for the rest of the value from the table, then this is all we got. So we have a total of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 different sample mean X bar. So that's how we construct the probability distribution table from the sample size. Now, again, the same example. Let's take a look at when you are rolling one die. Okay, so one row of a die. Remember, the outcome of the dice could be 1, 2, 3, or 4 only, 4 total. So when you are talking about the population, that means when you are trying to roll a die one time, then each of the value here has an equal chance of being selected. So number one has 1 out of 4. 1 out of 4 or 0.25, which is the probability of getting that change. The same thing to number 2, you also have 0.25, and then the same thing for the rest. So this is the histogram for the population. However, with the sample mean of the 3 rows that we discussed earlier, the 3 rows right here, the big table, 64 sample mean, then each of them, if you plot them, if you plot them, remember we construct the probability distribution table 1, 0.016. So when x is equal to 1, when the sample mean is equal to 1, we have 0.016. And then let's draw the next one. When x is equal to 2, x bar 0.156. Right, 2 is 0.156. So 2 is right here, 0.156 is right here. Now you can see that we are approaching the normal curve in this case. So the sample mean tends to approaching a normal curve if the sample size is large enough. So if the sample size is large enough, for example 30, 40, 50, then the sample mean x bar will be approximately normally distributed. The size of the sample needed to obtain the approximate normality depends mostly on the skewness of the population. So in practice, a sample size of the size n is bigger than 30 is large enough. So even though the population is not normally distributed, the sample size, the sample mean is still normally distributed. Now, for the case when the population is already normally distributed, then the sample mean will be normally distributed no matter of the sample size. But if the population is not normally distributed, then we are required to have at least 30 for the sample size in order for the sample mean to be approaching to the normal curve. So now it's time for us to introduce the central limit theorem. So let x bar be the mean of a large, maybe n bigger than 30, simple random sample from a population with the mean mu and the standard deviation sigma. Then the sample mean x bar has an approximately normal distribution with the mean of the sample mean is approaching to the population sample mean. However, the standard deviation is not. The standard deviation of the mean of the sample mean is equal to the standard deviation of the population divided by the square root of the n. N is the sample size in this case. Remember from the earlier slide, I mentioned that the sample means, variance, and proportion, they are unbiased estimator. That is, they target the population parameter. However, the standard deviation is not. It is the biased estimator. That means it is not approaching to the population parameter. Therefore, the standard deviation, they are not the same. You have another factor of the square root of n. Okay, let's take a look at this example. We have a sample of the size 24. We will draw from a population with the mean of 35 and a standard deviation of sigma equal 1.2. It is appropriate to use the normal distribution to find the probabilities for the sample mean x bar. The answer is no, because the population is not known to be normal and the n is not bigger than 30. We are required to have the sample size to be bigger than 30, and therefore we cannot be certain that the sample mean x bar has an approximately normal distribution. So remember here, the population has the sample mean and the standard deviation. They did not tell us if the population is normally distributed or not. If the population is normally distributed, then the answer would be yes, no matter of the sample size. However, in this case, the population, we don't know about the normality of the population, and the sample size in this case 24 is less than 30, and therefore we cannot be certain that x bar has an approximately normal distribution. Okay, let's take a quick look at the last example. Recent data from the US Census indicates that the mean age of a college student is 25 years, mu, with a standard deviation sigma 9.5 years. A simple random sample of 125 students is drawn. So this one here is equal to your sample size n. What is the probability that the sample mean age of the students is bigger than 26 years? So firstly, we know that the sample size is 125, which is bigger than 30. Therefore, we can apply the normal curve to this problem. And let's draw the normal curve. I know that I have the mean to be 25, and therefore the mean is at the center. I'm looking to find the probability of that sample mean of the student to be bigger than or greater than 26 years of age. That means I'm looking for the area, the portion after 26. This is the x bar sample mean value. Now, remember, the sample mean is an unbiased estimator. Therefore, the mean of the sample mean is approaching to the mean of the population, which is the same thing as 25 here. However, for the standard deviation of the sample mean, it is not the same thing as the population mean, because the standard deviation is the bias estimator, and we have to divide by the factor of n. And taking the population standard deviation divided by square root of 125, you will get 0.85. And now to find the area, we can use the standard normal distribution, which firstly you have to convert to the z-score. So the z-score of the sample mean, we take the value of 26 because we are looking for the 26 here. So that is your x, the sample mean of the x. Subtract the mean of the x bar. We found it here to be 25. And then divide by the standard deviation, we found it here 0.85. And then if you do that, you got 1.18. So 1.18 is right here. We are looking for the right area of 1.18. Now, we can use this is the positive z-score, so we can use the positive z-score table 1.18. 1.1 is right here. And then we need another 0.08. So let's go all the way to here. 0.08. The column 0.08. And this is 1.0 right here. So this is the area to the left of that z-score. 0.8599. Sorry, I think I read the wrong one. 1.0, this one. Yes, 0.8599. Okay, 0.8599. No, it's not. 1.1 is here. I read 1.0. So 1.1 is here, but we are looking for 1.18. So this is the number. Okay, this is 1.0 together with 0.08, so 1.08, and the value is 0.8810. That is the area to the left. So this is the z-score, and 0.8810 is the area to the left of that z-score. However, we are not looking for the area to the left of that. We are looking for the portion to the right. Remember, everything of the whole density curve, the area under the whole curve is 1. And then we got 0.8810. To find the rest of the right, you take 1, subtract that. And that is the answer, 0.119. Or the probability that the sample mean age of the students is bigger than 26 years old is 0.119, or 11.9%. Now we can also use the TI-84 graphing calculator to help you to do that. Now, if you are using the TI graphing calculator, you do not need to find the z-score. We are only using the z-score when we only have the table, because the table is only applied for the standard normal distribution only. So let's try to use the z-score, the calculator for that. All right. So we go to second distribution. This is the normal curve. So we go to normal CDF, cumulative area. Now we have the lower bound. So we start from we are looking for the area from 26 all the way to the right. So we type 26 for the lower bound. For the upper bound, you want all the way to the right, all the way to the right. So putting a large number should be 5 for the right side. So you may put like 99999, as long as you put a very large value. You want all the way to positive infinity, and in here, just put a 6 number of 99999. That should be all the way to the right. And then the mean, remember the mean is 25. And the standard deviation is 0.85. We are not using the z-score scale, therefore you have to change the mean and the standard deviation. And then it will give you directly the area to the right of the 26. Paste that, or if you are using the TI-83, then you have to type the function step by step like normal CDF, lower bound, comma, upper bound, comma, the mean, comma, standard deviation. Mean and standard deviation. And then close the bracket. And then hit the enter. And that will give me 0.119, which is what I got earlier here. So that's how we use the central limit theorem to find the probability of the sample mean in this case.